the director of the Revista Mexicana de Física, the research revista, educational, and the supplement. And he has received a recognition to his trajectory from the Mexican Physical Society, as well as other entities. So thank you, Alejandro, for being here and closing the session. And he will be talking about the relaxation time for quark-antiquark alignment of spin and global vorticity in a rotating QCD medium. Please, Alejandro.
Thank you, Alfredo. And thank you. Thank you for sticking all the way through at the end of this meeting. And again, for the benefit of some of our distinguished colleagues, I'll give my talk in English. Of course, I can fetch questions in Spanish if anybody wants to ask me in that language. So thank you for the introduction, Alfredo. It's a pleasure to be here, and thank you to the organizers for the kind invitation. The work that I'm going to report on has been developed along several years, and this is a list of my latest collaborators in this particular calculation. And what I want to convey to you is that the study of the properties of strongly interacting matter under extreme conditions are quite fascinating, and one of the frontiers to learn about these kind of systems from which we know little. And as probably you've gathered from all of these talks, the search for things that are new is always a motivation to continue. And what we want to do is to explore these kind of systems from several points of view. And as Alfredo mentioned, one of my ideas to do this kind of research is that we can gather information from experiment and try to put it together in such a way that we can understand these systems from a perspective of theory. So theory and experiment are always feeding back to each other. And so what I'll present to you here is an example of such feedback, which is positive, to try to understand what's going on. This has to do with the physics that you can study when you use machines that are built on Earth that collide particles, and in particular, they collide heavy nuclei. And when doing this, what you produce is a kind of matter that presents thermal properties. So you produce a statistical system. And so you can ask questions about what is the nature of these kind of systems when you have temperature, when you have density. And what you want to do is to explore the nature of this matter by varying this temperature and this density. You can achieve that by building very powerful machines, like for instance the LHC and the detectors that are associated there. Energies that in the center of mass of these colliding systems reach about TeV scale energy. But you can also do it by lowering the energy and studying a situation in which the nuclei that collide stop each other more than at higher energies. And when you do that, you study the situation in which what you have, the highest of the energy scales is the density. And so you want to explore the properties of matter, or of this kind of matter, in this very wide range of temperatures and densities. And for that, you want to look for probes that are messengers of the kind of matter that you produce. And this is what I want to do. So I want to look at one of these probes and then try to understand it first. I will present you the facts, what is being measured, what is the probe that I'm looking at, and then I will proceed to try to give a reasonable explanation of what is the kind of analysis using the techniques that we learn to explore these kind of systems to extract the information that this probe is bringing to us from these reactions. So you can imagine that these reactions are really complicated to analyze, and in fact, they are very complicated. So we need specialists from different fields, and in particular those that are able to extract these signals and then produce them in terms of experimental data, to which we then sink our teeth in and try to understand what's going on. So this probe in particular that I will use to exemplify is the possibility that quarks that are produced in these collisions, as you know, they have a property which is called spin. And so the question is, given the situation in which they are produced, and I'll try to show you why this is a special situation, in certain collisions, what you produce is that the matter that interacts starts spinning as well. And so what is the possibility, and you quantify this with a probability. What is the probability that the spin of the quarks that were produced, given the fact that they are moving in a rotating environment, their spins align in such a way that the probe that I'm going to look for, and this is the polarization of certain particle, also inherits that alignment of the spin. And this is a way to try to understand what is going on in these kind of situations. So let me move on and try to give you, it's difficult to see, I know, but let me try to give you some, oh boy, it's even more difficult to see. Anyway, so bear with me. What you have here is a cartoon in which a nucleus, which is moving along this line, two nuclei that are moving along this line collide. And after the collision, they recede from each other, they move away, and they leave in the middle some interaction region. Now, if the collision was not head-on, that is, the centers of these nuclei did not coincide along their trajectories, then the matter that remains there, when they collide, we call it a finite impact parameter. When they collide, parts of the matter that were produced start moving in one direction, the other parts start moving in this, well, they rotate. And so if this matter rotates, then the system that is produced there, which presumably also liberated quarks and gluons in the collision, is composed of these matter, spinning. Now, the spinning of these systems is one of the, that is the angular velocity for the spinning of these systems, is one of the largest for systems that we know. It can be quantified in terms of the unit of spin, which is h bar. And it turns out that the angular momentum associated to that is of this order. This is very large, so there are no other systems on Earth that are known to spin this fast. So the question is then, the spin-orbit coupling of these quarks with the angular velocity of this matter, is it enough to produce that the particles that eventually are produced by the strong interaction also have a signature of that interaction? And so this is a kind of problem which is not something which is exclusive from the world of nuclei that collide. In fact, this is a very well-known phenomenon which is called as the Barnett effect. Imagine that you have a ferromagnet, and then imagine that it is above the Curie temperature in such a way that the spins are not necessarily pointing out in a single direction, or preferably in a given direction. So now, have this piece of material, and then have it rotate around a given axis. If you wait long enough, what you will find is that these spins, these elementary spins, are all aligned. And so the question is, how long does it take to the system, in this case this ferromagnet, to go from this state to this state? Now, you can imagine that if this ferromagnet is rigid and you make it rotate, then eventually you will have it go from this situation to this situation. So you can wait as long as you want. But in our case, in which we collide nuclei at a given energy, there are several phenomena taking place. In particular, what happens with these collisions is a kind of an explosion. So you see two nuclei come in, and they form this matter, but this matter expands. It's like, you know, a little bang. And so it's not enough to just wait forever. If we want that this situation happens, go from here to here, then we need to have this happen within a certain time, which is less than the lifetime of the system to break apart. So this is the question I want to answer. How long does it take to strongly interacting matter to align the spins of the particles that were produced in such a way that within the lifetime of the system, you can produce the particles that eventually you detect and then trace back the signatures of this rotating matter. And this is what I want to do. So let me show you facts. First of all, I need to target a given particle, which is or could be easy to follow the spin. And that particle is this hyperon. It's called the lambda hyperon. It's made out of 3 quarks. 2 of them are the lightest ones, U and D, and the third one is an S quark. So you know that this particle needs to be produced. It was not present when 2 nuclei collided, because nuclei are made out of neutrons and protons, and they don't have strange quarks as their content. So if this particle was produced, it was produced as a consequence of the collision. But then it decays. It takes a long time to decay because the process to decay, for decaying of this particle is a weak process. In the scale of strong interaction times, this is a very slow process. So eventually it leaves the region where it was produced, which is just of the size of 10 to the minus 22nd meters. And then it flies away a little bit, and then it decays. And when it decays, it produces mainly protons and pions. Negatively charged pions, positively charged protons, because this particle is neutral. The nice thing about this particle is that the decay products, mainly the proton, mainly moves along the direction of the spin of this particle. So if you detect the protons, or the angular distribution of these protons, then you can measure the polarization of this particle, this lambda. And so these are some of the numbers that are associated to this particle. And so this makes these kind of particles excellent probes to try to follow what happens to the spin of the constituents. So imagine, and this is what I'll do for the rest of the talk, imagine that the particle, this lambda, which is, again, made out of 2 light quarks, U and D, and an S quark, imagine that the polarization of the lambda, or the spin of the lambda, is carried by the strange quark. This is not that far-fetched as it could sound, because typically these U and D quarks, which are the lightest ones, could be thought of as being made of making up a diquark. So the spin properties of the particle will be basically those of the strange quark. So if that's the case, then let us see what are the facts. And the facts are, that the polarization has been measured. And you see, this, of course, made it to Nature, but it made it all the way to the cover of Nature. And this is an experiment which was made in the US. It's called the Beam Energy Scan program of the Relativistic Heavy Ion Collider. The STAR experiment in particular took these measurements. And they have the capability of moving from high energies, these are 200 GeVs in the per nucleon, in the reference frame of 2 nucleons colliding, all the way down from 200 to about 10 GeVs of this energy. And so this is the collision energy. And notice what happens. The polarization, which is this vertical axis, and which is shown in terms of a percentage. In other words, how many of the total particles that are produced show that their spin is aligned in a given direction. The polarization exists. It's different from 0. 0 would be somewhere here. And here, as you lower the energy of the collision, then you see that the polarization increases. The red dots, which may be difficult to see, to be seen from the back, but these are red and these are blue. The red dots represent the polarization of the anti-lambda. It's the antiparticle of the lambda, which is made out of anti-U, anti-D, and anti-S. Again, we may imagine that the spin of this particle is carried by the anti-S. So you see that it's really striking that this polarization for the antiparticle seems to be much higher than the polarization of the corresponding particle, of the lambda. But also striking is the fact that this polarization rises with energy. So this is a very interesting regime of energy of the collision to be studied. And in fact, I am a member of a collaboration which wants to do this experimentally. This is called the multi-purpose detector. It's being built in Dubna as we speak. And we, part of our program, our physics program, is strongly motivated by these kind of measurements. We want to know whether or not these discrepancies exist there. What is the trend of this polarization when we lower the energy, and we are going to be exploring that energy domain. And so we may provide answers to this kind of question. So, well, there's more information here. If you are interested, I can tell you more details. But these things, yes, it's moving. But there is, of course, it's not the end of the story. It's interesting in many aspects because, see, there are other experiments that have also provided information on this polarization. They have done it for lower energies as well, but for different systems, also heavy systems. For instance, silver and silver instead of this is done for gold and gold. And then you can see that the polarization is still not showing any signs of decreasing. So it keeps increasing. Now, unfortunately, these measurements are only for the lambdas. They are not made for the anti-lambdas. So we don't know what happens here for the anti-lambdas. But again, the message right now to take home is that this polarization keeps on increasing as we lower the energy. Of course, we will reach a threshold for the energy to produce those particles. So when we reach it, of course, we won't have those particles and therefore no polarization. But see, close to threshold, this number is still high. There are many explanations, of course, many possibilities, but let me keep going describing the facts and make this move. Okay, so see, this is an interesting plot in the sense that if you exclude the point where the polarization of the lambda was, sorry, the anti-lambda was really large compared to the lambda, then by looking at the polarization of these particles from, say, about 11 GeVs per nucleon up to 200, what you see is that the polarization of the difference, so you take the polarization of the lambdas and the anti-lambdas, take the difference, and then you see that this is more or less consistent with 0. So it means that the polarization of lambdas is as large as the polarization of anti-lambdas, but with large error bars, of course. So this calls for doing these kind of experiments also at the same energies with another setup in such a way that we can either confirm or bring these error bars to lower values. So why did the collaboration exclude, this is the star again, why did they exclude the point at 7.7? Well, perhaps we should ask them. We should ask that collaboration to tell us, but probably they don't trust very much their analysis in this region anyway. So you can see here that within this energy domain, this difference of polarization seems to be consistent with 0. So what do we do when we have this kind of observation? So this is a trend that I try to teach my students, and I enjoy it a lot. So I'm a theoretician, And I see these kind of results, and then I think, oh, there is a challenge here. So let's try to tackle the challenge. What is the physics that I know? What is the physics that I may learn, even if I don't know the whole physics that is behind these observations? So the pattern goes as follows. You take a look at the observations and then try to make up something that may explain it. And typically what you want to do is something that nobody else has done before. So to try to come up with an explanation. Of course, you run the risk of building a model which doesn't make any sense, but if you are guided by how this model could be applied to some other circumstances, then you learn that whether or not this is a reasonable description. So let me just make a summary of the observation. So there is an apparent rising trend when we lower the collision energy for the polarization of these particles, although with a large uncertainty. And it could be that if we produce quark-gluon plasma, this component can be the responsible for the polarization at large energies. But at low energies, it may be that we also have the contribution from processes which do not produce quark-gluon plasma, and that only describe the interaction between nucleons that are participating in the reaction without liberating the quark-gluon degrees of freedom. And so the last observation is that if you exclude this measurement, this difference in polarization seems to be consistent with zero. So how do we put that together? Well, let's build a model, and then we come to the theory to try to explain it. What is the model? If you have a collision which is not head-on, in other words, it happens with a finite impact parameter, then you see that the collision region is still different in density. This is because nuclei are denser from the middle and less dense at the edge. So when you collide the densest parts of the nuclei, what you get is a dense region, and here it is represented by this red dot. But when you move to the edges of this interaction region, this here represented by this yellow and this green, then you get a less dense situation. So for a given energy and a given impact parameter of the collision, you can produce quark-gluon plasma here in the densest region, but here you will have the reaction, which is mainly nucleon-nucleon collisions. And so to distinguish that, I'm okay. To distinguish that, then you can separate the particles that are produced in this reaction to build the polarization. So as I said before, the polarization of these particles is the difference of the particles with a given spin projection and the opposite spin projection with respect to a given axis. And here the given axis is the angular momentum axis, which is perpendicular to the reaction plane. It's just a definition. The reaction plane is the plane which is made out of the direction of the impact parameter and the direction of the beam, which is this one. So in this cartoon, the reaction plane goes along this direction. So you measure the polarization that goes along this direction, and the opposite one, you construct this difference and then take the sum as the total, and then this is the definition of the polarization. So let me break up this polarization in two components and see, this is the model. The two components are the ones that come from particles that come from these two distinct regions. And here I have to go back, sorry. Again, and something is going wrong, and could you help me there in the help desk? Oh, here, thank you. So, let me break up that polarization into two pieces, okay? So, these pieces are the particles that are polarized that come from the QGP. This is that, and then particles that come from the recombination zone, which is this lens region. And so this is the total number of particles with a given spin projection, and you subtract the sum of those two and divide by the sum of these two processes here and this here. So you can do a little bit of math, and then to come from here to the polarizations, you end up with a model that requires knowledge of this difference, the polarization of the given particle or antiparticle, when these were produced in the QGP, divided by the particles that were produced in the edges, which is called here rec. The same thing for the antiparticle, for the anti-lambda. And so you would like to model these components. And so be patient here. I can give you more details if you want, but this modeling involves this difference. You see, I call this difference the number of particles produced in the QGP with one polarization minus the other one divided by the total. I call that ratio Z. And the Z bar, the same object for the particles, for the antiparticles that were produced in the QGP. So it's same definitions, but this is for antiparticles and this is for particles. And so you come up with an equation that looks like this to describe the polarization. So this object is important. And there are other objects here, which I'm not going to talk about right now, but I just want to bring your attention to the fact that I need to know something about these objects here, this difference. These are what we call the intrinsic polarization. You see, if the particles come from the QGP, so they will be polarized, and this is a measure of what is their polarization. And assuming that the particle that is eventually detected keeps the polarization as the one that came from the QGP carried by the S quark, then this is an intrinsic polarization. Intrinsic in the sense that it came from the intrinsic process of producing the particle that eventually is measured. So I want to compute that. And why is this important? Well, it is important because, see, imagine that I have a given number of particles which are non-polarized. Then if this process of spinning of the reaction zone transmits polarization, then after a given time, which is t, I will have particles that are polarized. And that will be given in terms of the intrinsic relaxation time. So if I want the particles polarized, I want to extract them out from this non-polarized situation to a polarized situation, and therefore I have to start with one, and then as I populate the polarized state, I have to extract. I'm sorry, this is a symbol which should have been a minus. I need to subtract this factor from this, and so this corresponds exactly to what I'm looking for. This is the polarization. This is intrinsic polarization, and it has to do with this important quantity, the relaxation time, and the lifetime of the system. So again, in the cartoon that I showed you at the beginning, if this spinning system breaks apart, I need to see whether or not the polarization processes were able to align the spins within a time which is smaller than the lifetime of the system. So you can see here, if the lifetime of the system, this is a minus again, if the lifetime of the system, which is this delta tau QGP, is very large, so this guy here divided by a small quantity is large, and so the negative exponential will be small, and so the polarization will be total. I'll have just a 1 here. Whereas, if this lifetime is small compared to this tau, then this factor is small, and the exponential is close to 1, and so 1 minus 1 is 0, so the polarization is 0. So access to information of this relaxation time gives me at least a handle on whether or not it is possible that the vortical motion gets transferred to the spin of the particles. And so this is what I want to compute. How do I do it? Oops, it's difficult to see here, but I need to do some calculation, some modeling it's involved. And in order to do that, since I'm a theorist, I know techniques that come with the name of quantum field theoretical techniques. And if you put temperature on these techniques, you do quantum field theory at finite temperature. And so you can compute in a thermal environment these objects which are, for instance, these relaxation times. They are related to total reaction rates. And the total reaction rates are given in terms of Feynman diagrams that give you the probability of some process to be produced. So you need to put the ingredients together, have patience and perhaps a couple of students and very motivated postdocs. And so you plow through and compute these objects. And the object I want to compute is the self-energy of a propagating quark within this medium. So this may sound very technical, but it's not. I just want to know, through this Feynman diagram, what is the probability that a particle which is moving in this vortical motion and has a spin 1/2, like these quarks, after some time, make this rotating motion, make this particle to point out, the spin of this particle to point in a given direction. So there are some techniques. You need to know, for this process, how to describe the propagator of a particle that is moving in this environment, which is rotating. And that object requires some calculation. So the calculation is simple if you know what are the techniques, and these are actually quantum mechanical techniques. There is not much secret on this. So in order to compute the Green's function, which is this object here, you need to know what is the Hamiltonian of your system, and then the Green's function will be given in terms of this is the time evolution operator associated to this Hamiltonian, because it satisfies certain equation, which is an evolution equation, with certain boundary conditions. This is the message I want to convey to you. So if we know the solution, then we can find, in other words, the problem is to find this object here, which is the time evolution operator, to compute this Green's function. So once you have the Green's function, it is a very nice problem, because see, the solution, formal solution, is this equation here. It looks nasty because the Hamiltonian is in the exponent, and it is acting on this delta function. But the nice property is that the delta function can be expanded as this exterior product of solutions of this Hamiltonian. So if you put this formula inside here, then you can act with the Hamiltonian on these functions, and then all you have is in the exponent the eigenvalues. So you solve your problem. So this is the beauty of these mathematical techniques, and you have the solution given by this simple formula, and then you apply it. How do you do it? Well, if you have a rotating environment, this is similar to a system that mimics gravity. So the metric is changed from a flat spacetime to something like looks like curved spacetime. So there are components of the metric which are different from the ones in the diagonal. So you just write down for a rigidly rotating system what is the metric, and it happens that this is the metric. And then in order to put your system, which is these quarks moving in this environment to describe and find the wave functions, then all you do is to replace the ordinary derivative by this covariant derivative, where these guys here are called the affine connections, and they are just related or obtained from the metric. So again, you see, these techniques allow you to describe your problem in simple manners. Okay, so you solve Dirac equation with this technique, and you find the solutions, and since you have the solutions, and you have the other technique, that allows you to find the propagator by applying this time evolution operator technique, then you have an answer. And let me spare you the details. Just give you the final answer for this propagator. And the answer is here. Well, not here. The next one. Come on. This is happening because it's the last talk of the Congress. So you see, the battery is out. almost out. Come on. Okay, here. Here, okay. This is the answer. Looks simpler than what we can think, because see, it looks like an ordinary propagator for a Dirac particle, but now what is emphasized here are the spin projection operators here. So there is a spin projection operator for the up direction and a spin projection operator for the down direction. And well, of course, these have to be accounted for, but it's simple enough. So what is the physics? So let me extract the physics out of this. What we did were approximations to get to this nice and simple analytical result. The approximations is that we know that we cannot have a rigidly rotating body with an arbitrary radius. You see, if I move like this, even if I move slowly, if my radius is very large, the angular velocity at the tip, far away, will be moving faster than the speed of light. That cannot happen, and that's called causality. So I need to impose causality conservation, and that means that I need that the angular velocity times the radius is less than 1. This is the causality condition. But on the other hand, in order to get to the result that I just showed you, I needed to make an approximation, and this is the approximation of rigid rotation. So the particle I'm looking at will be subject to rigid rotation. In other words, it's not breaking out, the system is not breaking out, it's not expanding radially. So as long as the angular velocity is large enough, then I can do that approximation. So there is a window of applicability of this model. Again, once, you probably know, as physicists, we need to, if we are modeling, we need to know where our model works, and the region where it works is the situation in which omega is smaller than the inverse of one of the radius, but large enough so that we have a window of applicability of this result. Anyway, so you have to keep in mind this. When doing physics, it's important to keep, to know what are the limitations of your model. Another limitation, which is in this case analytical, is the use of the particle that carries the interaction, which in this environment are the gluons. So the gluons are described also by a propagator. They have certain properties. This is quite interesting when they are in a thermal medium. A gluon, which has only 2 spin projections, has 0 mass, develops a thermal mass, and the thermal mass is given here. This is the square of the thermal mass. This is a nice computation in thermal field theory. It is proportional to the temperature, and some objects which have to do with the group that describes QCD interactions. And it also develops an extra polarization direction, so it's not only 2 polarizations, it's 3 polarizations. 2 of them are longitudinal, and 1 is, 2 of them are transverse, and 1 is longitudinal. Anyway, so those of you that may be interested on these details, I can provide them to you. And so you come up to the computation of the object in thermal field theory, which is this diagram, this self-energy diagram, and then you put in the elements, sorry to go fast, and so all I want is then compute this relaxation time. So I have computed through that diagram this total reaction rate. I need to weight that in the phase space of my reaction, the whole volume where I'm working at, and that is given by this phase space integral right here, which is multiplying this volume. The volume is the volume that corresponds to 2 spheres that overlap with a given impact parameter B. And so all we want then at the end is something that is difficult to see here, but it's the inverse of this object here. So the relaxation time is the inverse of the total reaction time. So the stronger the reaction is, the smaller the relaxation time. That is understandable. Because see, if the interactions within this medium are strong enough, they will produce that particles align in the direction of the orbital angular momentum. And so let me just show you the results. These are preliminary results. And We need, of course, to model what is the relation between the chemical potential and the temperature for these kind of systems where we are exploring finite baryon chemical potential. And we need to see or to say what is the angular velocity. We take this from the literature. This is one of the references. It's been done in several others. And this is a result. So the answer for those of you who were wondering whether or not this is possible, the answer is positive. Again, this is preliminary, but you see, what I have plotted here in the vertical axis is the relaxation time. I'm looking at quarks first. So in other words, I'm looking at lambdas that are polarized. And I do it as a function of the temperature, where the temperature and the chemical potential for baryon matter to be produced are related. And then you see that depending on the chemical potential, this is a larger than zero chemical potential, 0.1 GeVs. And this is for the zero case chemical potential. This is the blue line. So the blue line is this one. This is the red one. And so these quarks are thought to be produced for temperatures which are around this regime. And if you go, then you look at these relaxation times as a function of temperature for these two situations of chemical potential. You go here on the horizontal axis to see where they cross the vertical axis and read what is the relaxation time. And within all of these approximations, I know that these are, well, I mean, I spelled them out. You see that the relaxation time is of the order of 1 Fermi. And the lifetime of the system is believed to be between 5 and 10 Fermis. So this is very encouraging. So it means that this rotating system does not break up before it translates its information to the spin of the particles. We can do this also for antiparticles. And so these are the antiquarks. For the antiquarks, it's less favorable. So again, for these temperatures, the relaxation times are of order 2 Fermis, but still within the lifetime of the system. So we were able to compute this, well, fundamental quantity for the description of these systems. And with this, I just want to conclude and make some summary. So the relaxation time that we wanted to compute is an essential ingredient to see whether or not it is possible to transmit rotation to spin degrees of freedom. And if you employ these techniques of field theory, you're able to compute this relaxation time, and the result is encouraging in the sense that the alignment may seem to happen within the lifetime of the system before it breaks up. And so now what we need to do is to explore what are the consequences for the description of the polarization of the lambda and anti-lambda particles. And with this, I conclude, and I thank you for your attention.
Thank you so much, Alejandro. So are there any questions?
Was too heavy.
Was too heavy.
Will it be possible to use your results, or will it be useful such results in some pentaquark model? Yes, it's a good question. The pentaquarks are produced. The problem we face sometimes with pentaquarks is that, or tetraquarks, is that these are combinations of either a state in which you have, for some reason, bound together 5 quarks, or you may have a molecule. So my intuition is that if you have the first configuration, then, and if the spin is carried by one of these, only one of these quarks, then it could be. If not, then I think that you need to make a heavier analysis. So in other words, for any particle whose spin is carried by one quark, these results may be useful.
Okay, more questions? Yes, Juan.
One of the most fantastic objects in nature is pulsars. So these formulas could be applied to some exotic quarks in pulsar quark stars and something like that are rotating very fast, even relativistic velocities.
Yeah, that's actually very nice because, again, pulsars are thought to be, as far as I remember, neutron stars which may have an inner nucleus which is made out of quark matter. They call it strange quark matter in that sense. And as far as I remember, the hyperons, lambdas in particular, or sigmas or cascades, contribute in the right direction to explain the existence of these objects which are above 2 solar masses with radii which are smaller than thought. And this is made out through the modification of the equation of state. So it is an interesting question that you raised, because see, the point is, how is that the energy momentum is balanced? And typically, you only care about the production of these particles, and you do it in terms of static conditions. You never take into account this motion, which is really important in these objects. So these are fastly rotating. So some energy, if this is transferred to spin degrees of freedom, some energy goes into the alignment. And that can also influence the equation of state. This is absolutely a very interesting question. Thank you, Juan.
Okay, any further questions? Any comments? Si alguien quiere preguntar en español también, con toda la confianza podemos ayudar a traducir. Well, if not, let's thank Alejandro
Gracias,
again.
gracias a todo el mundo.